It's always so inspiring to see actual practical use cases for the technologies that we have today, coming from entertainment. Makes you envious for the utility of what is being shown. So what we're gonna talk about today is the road to making Gaussian splatting dynamic, to capturing the next generation of volumetric videos and such. So let me share my screen, and here we go. Basically, the path that we were on showed us that in the recent years there was a very inspiring rise of truly efficient photogrammic 3D technologies that allowed us to do 3D capture with consumer-grade hardware. And with the rise of first nerves, we saw the potential of creating, of capturing reality in truly photorealistic fashion. So we could truly appear inside of realistic 3D environments and opening up new avenues for the 3D production, for application in games and other media. But while we're still learning about the potential use cases of nerves or neural radiance fields, another technology came up, and that is Gaussian splatting, the reason why we're all here today. And with Gaussian splatting, we got improved visual quality, and it was so much more efficient than nerve that it showed potential for application in real-time scenarios like maybe video games and integration to websites and such, mobile device viewers. There are a few very interesting projects today that allow you to browse the Gaussian splatting scenes in VR, which is an amazing experience. But still, with all the technologies, of course, we're in early days, and we are yet to see them reaching the kind of quality and accessibility to make them truly mass audience, even with static content. But looking into the future, of course, when we started seeing some of those first amazing 3D scenes captured with Gaussian splats, many of us, I know, I was among the first to start thinking, okay, but can we now capture that as a video? Can we try to push our entertainment in the next dimension, so that we can start watching videos in 3D, where we can pick our own angle from which to look at the all the amazing content that people are creating today. And some of the very interesting works started to appear as in specifically in academia, demonstrating the potential of Gaussian splatting for dynamic content. But still, there are some challenges, and that is we still, for capturing something as a dynamic Gaussian splatting scene, we need a whole load of high quality cameras. We need a lot of compute resources to process the results. There are still some rendering artifacts that can happen, especially under varied lighting conditions. There's a lot of issues with if we're capturing several people, people are overlapping each other, and what do we do with the gaps that are being created? And the biggest challenge that we're going to focus today on is the size. The thing is, Gaussian splatting scenes, they weigh a lot. And if we approach this problem as sort of like a frame by frame flipbook kind of animation, we're gonna get hundreds of gigabytes, if not several terabytes of data that would be needed for just 1 hour of a scene. And of course, that's not practical. No one's gonna download a couple terabytes just to watch 1 hour 3D volumetric video. And of course, another problem is with the integration because, again, these are the early days, and we're still tackling the problem of where do we actually put this content? Do we put it on the web? Do we put it in the game engines? Do we create independent apps that specifically focus on this kind of content? So these are the open questions today. We've been tackling with some of these fundamental issues of dynamic Gaussian splatting since late last year, and came up with a novel approach that in some ways shift our understanding of representation of Gaussian splatting. The things that we focused on is sort of the pillars that we wanted to build the technology on is we wanted to support interactive streaming so that people with mobile devices can watch this kind of content. It needs to be energy efficient so that, again, it works on the mobile devices and XR devices. We needed to improve image quality so that you can look at the scene from any angle and you're not going to be getting too many artifacts in the process. And it needs to seamlessly integrate with classic 3D technologies because obviously we, as soon as we start getting this kind of content, we would definitely want to put dynamic lighting. We would want to put some kind of interactivity in, and that would require us to combine the new world of photogrammetric 3D with some of the sort of old school technologies. So talking about the compression, with the technology that we were working on, we achieved a result of almost 97% compression over the uncompressed Gaussian splatting frame. You can see the difference in quality between the frame on the left and frame on the right. A little hint, there's none. So we don't lose anything in terms of quality, but we get pretty efficient compression where we get only 8 bytes per particles, per single particle or a single splat. And moving forward, of course, talking about the ways to actually get this content to the end users, we focused our efforts on making it streamable. And the way we approached it is quite similar in some ways to the video codecs that rely on so-called keyframes. So instead of doing a frame by frame where we send the entire data on every captured frame, we rely on the keyframes where we know that there was the most change compared to the previous keyframe, and we do delta compression. So we only send the data that is required to replicate the changes that happen over time. And some of the other techniques that we apply is that we segment the scene. We separate the environment from the action. So if there's city scene or something, we separate the blocks of that scenery that are not changing much or at all, and we don't update them at all. We only focus on the elements of the scene where most of the action happens, specifically people, if we're talking about some maybe theatric or cinema-like content. And as of today, we only required about 10 megabits of bandwidth for streaming of 2 or 3 people performing in Gaussian splatting environment. And of course, the static splats don't consume any additional bandwidth. So I'm going to show a little video. The video is going to demonstrate some of our early experiments in that area. We took a data set from Panoptic. I'm sure many people in the audience have seen these videos before, and we put them in Unreal Engine. So here's the original footage. It's only a 360p resolution, and here we're putting that in one of the template Unreal Engine scenes, and we can see the result in action. And I'm just gonna show that again so that we could focus on the lighting and shadows. You can see that both person in the scene, they drop shadows. The ball drops a shadow. There's self-shadowing. I'm going to show a bit more extreme example now where we do some dynamic work with the light and shadows. So you can see it all working together. Here's before and sort of here's the after. And just a little showcase scene again, these two gentlemen being put in the forest scene from the Unreal Engine 5.3. Again, this is a low-res content. We are now working on our next showcase demo with the high resolution, and we hope to have it available for demonstrational purposes next month. And going next, so as I've mentioned, on our path towards achieving efficient 4DGS animation, we had to rethink a lot about what Gaussian splatting implies. We pretty much took it to the full cycle of capture and reconstruction of Gaussian splatting and rethought every step of the pipeline. From the capture itself to reconstruction, compression, loading, streaming, and so forth. Some of the problems that with the current approach to 4DGS don't allow us to achieve efficient results is, first of all, lack of hard surfaces. This was actually touched upon during the previous presentation that Gaussian splatting, they're just, it's a new way of reconstructing point clouds without relying on hard geometry. But as a trade-off, we don't get any surfaces. And when you try to reconstruct even a single frame based on the same data, you're never going to get deterministic reconstruction of that scene. So the splats are always going to be different. Even if you're like not changing anything, you just run your favorite Gaussian splatting software, and you're going to see that maybe one time there's a single large splat that's gonna be used for some kind of a reflection somewhere far away in the scene. Another time there'll be a whole bunch of splats configured randomly. Imagine if we approach it the same way for animation content, it's gonna be way too chaotic to efficiently compress because we don't have anything in common structurally between one frame and the next one. Even if there was no real movement or happening between those frames, they're going to be way too different to apply any efficient kind of compression mechanism. So the method that we introduced here, we internally call it rainbow foam. You might ask why foam? It's because we actually, it's similar to how the foam actually comes to be. Imagine if we take a bunch of splats and sort of like foam them together in a new shape. That allows us to achieve a much more deterministic reconstruction frame by frame. That allows us to avoid artifacts like we're seeing on the frames below. And of course, as a result, we get better quality and better compression ratio, because now we know what part of the scene goes where. We know the structure of the scene, and we can do the delta compression efficiently. So again, the focus here is on stabilizing volumetric reconstruction. The current solutions, they use what is called gradient descent as part of the reconstruction progress, which is not very efficient when you're dealing with non-deterministic data. And there's another way, like with the nerves, where you apply machine learning models to do the reconstruction. But again, you're building chaos upon chaos, because first of all, you get this non-deterministic reconstruction, and then you pass it through the AI, and you get the even more randomness in the process. So with higher stability, we get higher efficiency. So on the with the rainbow foam, besides the appearance of the hard surfaces and better compression ratio, some of the other benefits that we get, we can much more efficiently combine that with well, sort of old school graphics techniques. We can apply ray tracing, we can apply ray trace global illumination. We can make it work within the same scene with other content, be that something in nerve, in Gaussian splatting, something manually created, some 3D geometry, generative 3D assets. They all start to work together in single scenes. So that opens up opportunities to use animated content within games, within movies, and many other media. So here's a little demonstration of this in action. What you're actually seeing, this pretty gentleman on the right, it's obviously not something we captured with Gaussian splatting in the lab. No, we don't deal with such creatures in our work. This is a polygonal character, but you can see that in the scene, he fully integrates in terms of lights and shadows. He drops the shadows on the 3D capture. He's being lit by the environment with ray tracing, and there's much more opportunity for us to create cross-media content that way, where we don't just rely on the stuff that's being captured, but also can create animated content where maybe people interact with props that came from 3D assets, or maybe appearing in generative 3D environments. You know, there's a lot of potential there. So generally talking about the next steps for animated Gaussian splatting in general, not just with our rainbow foam approach, some of the key areas for improvement is definitely reducing the needed camera angles. In our experiments, we've used about 40 cameras for efficiently capturing the action. What we are focusing on right now is on performing in painting algorithms on the content, so that we could use less cameras and just generate the angles in between. again, consistently, which is the key for proper reconstruction. We believe there's potential for implementing skeletal animation, and there's a ton of very interesting academic works today. Some recent works by Apple, by Meta, that doing interesting stuff with trying to make Gaussian splatting content animatable with any kind of standard skeletal animation methods. Of course, PBR is important in achieving the more of the realism in different lighting scenarios. Handling dynamic backgrounds where we're dealing with animated content that is being put in the captured city scenes and so forth. Generative in painting is also important for compensating overlaps that we mentioned before, like when you have a complex dance scene. Imagine you're capturing some kind of choreography and people are touching each other, they're overlapping, and we need to fill that data. Otherwise, the whole point of watching scenes in this 4D format falls apart, because you're going to start noticing the gaps in the data rather than enjoying the experience itself. Then talking about the segmenting and tracking entities, this is important from our viewpoint for compression. Like it's been critical for us to know where the action is happening in the scene, so that we can only stream the actual changes and be very reasonable in terms of hardware and bandwidth requirements for the content. And getting to our project, we call it vertical volumetric streaming. We plan to present it by the end of this year as a platform where people could watch the content recreated with rainbow foam, or I hope we come up with a better technical name for the technology, where you'd get all the benefits of hard surface, of dynamic lighting, of ray tracing, and being able to watch all kinds of media from sports to theater, maybe some comedy sketches, or pretty much anything you can imagine that goes today on TikToks and YouTubes. This can truly become available in this new 4D format, which we're very excited about. And yeah, I sort of was worried that we have too much information, so I jumped slide by slide, I think overly quickly, but let's stay in touch. We are really excited about being part of the Gaussian Splatting community. It's amazing to be there during those early days where we all together explore the potential of the technology, find new use cases, find solutions for the pitfalls, and let's stay in touch. You could find my personal LinkedIn or Twitter account, and of course, I'm available over email. So if there are any questions, I'm more than happy and hopefully ready to answer them.
Thanks a lot, Ivan. A really great presentation. And for the record, I like the name Rainbow Foam. I'll be a little bit sad if you change it.
Okay.
So a question from us was, did you develop Splat Squeeze yourself with a novel approach, or is it like an improvement of other techniques like compact 3D or compressed 3D Gaussian splatting for accelerated novel view synthesis or something?
Unfortunately, we had to reinvent the bicycle, which is sort of ironic, considering that bicycle is sort of like the the default Gaussian splatting scene. So yeah, we had to rework every step of the pipeline, and the only reason why we come up with this rainbow foam name is because at this point we don't use anything from the original publications on Gaussian splatting. We use a Latin principle because it's all been starting with nerves moving in a very interesting direction, and with Gaussian splatting providing a truly efficient way to represent this data. But for our purposes, we had to rework the very primitive that we use for reconstruction. And that's, again, where the foam is coming from.
Okay. And then I think so Barnabas has asked a question, which I think a lot of us are asking, are thinking, which is how could the Gaussian splats throw shadows? How do they do that?
So the video that we've seen today does not yet use the rainbow foam. So it still uses sort of like in-between solution, because we published that a few months ago. And it works pretty much the same way you would approach self-shadowing with particles. And it's you utilize the shaders. You do we used Niagara specifically in Unreal, and we built the shadows in the rendering pipeline, but based on standard Unreal particles made possible with Niagara.
Okay, and Sebastian Stent said he also likes the name Rainbow Foam. And because he agrees with me, I've got to ask his question, which was that would it be possible to combine real-time Gaussians, such as a scan of a person's body with a scan of their face?
Yeah, very good question, because this is exactly what we're testing. We have done a sample recording of a person singing, and we want to do a really close portrait view on the performance. And in this whole rig, we just don't get the kind of resolution needed to do portrait shots, what we captured. So we did a standard photogrammetry shot of the head of the artist. And part of our experiment right now is to do this swap of lower resolution head that we get as part of the full performance capture, and swap it with the high resolution scan that we achieved with in the standard DSLR sphere that is used for old school photogrammetry.
Okay, and there are a number of questions about sort of the capture techniques you're using, such as what cameras are you currently using for your data set? Are you working on creating new footage? And let's see what other questions. I think those are the sort of the main questions people are asking about. And then, sorry, another question was, would it be possible to use a technique similar to X-grids, combining LiDAR with visible light cameras?
So at this point, we're not focusing on professional grade hardware. Our focus is on lowering the requirements for the capture as low as technically possible. Ideally, what we want to achieve is that if you have a laptop at home and maybe an iPhone or an iPad, you put those three cameras that you have on you around yourself, or maybe like in 180 kind of setup, and the rest is filled with generative AI, sort of like in painting for the missing angles. So we don't do any work with LiDAR. We specifically focus on simplifying as much as possible. One of the recent recordings we did was with the GoPros. Honestly, it wasn't a success, but that was purely our fault that GoPros have very aggressive noise reduction, and we didn't account for that. So moving forward, we know that we need to try to get, even with consumer grade hardware, we need to get raw footage. And the more recent recording that we hope to show in a month was recorded in 12-bit color. We believe that by increasing the accuracy of color capture, again, the quality of reconstruction would vastly increase, even if you can't tell just by looking at the difference of the material with the naked eye.
Cool. I think there are at least two questions asking about surfals. So I think one of them I've lost, but the question is basically, how does your work compare with Gaussian surfals? Are there any similarities in the approach? And then there was another question around, is your method similar to some technical papers around converting 3D GS into flattened ellipses, such as Gaussian surfals?
No, actually, we plan to publish more about our approach. I wouldn't be the right person today to answer this question fully, but we do plan to share more technical details, which would explain the kind of difference that we have with surfals.
Okay, fantastic. We're a little bit over time, but let me just see if I can find one more. I guess this is a question that's popped up. Among other 4D GS approaches, which papers do you find most interesting?
Many of the recent publications showed a lot of promise in solving this or that issues in terms of dynamic reconstruction. Some show great results in compression. Some do increase efficiency by a lot. We even are seeing papers today that make nerves so much more efficient that we couldn't even imagine like a year ago that you could render nerves with such high performance. But the problem, again, coming to us reinventing the wheel, is apart from showing academic breakthrough, if we want to focus on making this a viable product for mass audience, we sort of need to solve all the problems at the same time. Of course, there's a trade-off. Of course, you can find a better single frame compression than we do. Of course, you can find a more efficient reconstruction, but maybe that reconstruction would limit you to 180 covering of the scene, and you wouldn't get 360, which again was very surprising to us when we first entered this area. Papers started to appear that showed very good results. Like I'm sure you've all seen the paper that used the flamethrower near a garage, and very impressive results, but you can't apply this method to doing a 360. So we sort of had to just leave all those papers be and go our own way, which again, compared in individual areas may fall short compared to state of the art in terms of academic research available today, but it still brings us closer to making an actual product, an actual service that people can use. And that's been our main focus on actually bringing this to the end users.